please give us a warm round of applause for Christoph.
Excellent. Okay, I'm Christoph Berkemeyer, I'm a physicist, and today I would like to talk about long-distance quantum cryptography communication. It's the same. So, at first I would like to give a small introduction, then I would like to talk about quantum communication, then about extending the reach, and finally about the quantum repeater. So, the introduction. Let's assume we would like to communicate in secrecy. It would be preferable if you can use a provable security, and for provable security we need the one-time pad. The one-time pad is a very simple symmetric encryption algorithm, and it was invented in 1882 by Frank Miller, and later, I think in 1970 and 1980, reinvented. As you can see here, excellent. As you can see here, there is a plain text, there is a key, modulo the alphabet. The alphabet here is 2 because we are using zeros and ones, and if we just apply this machine, we're getting a ciphertext which is not decryptable. For a secure application, we have got some requirements. We need a random secret key, we need a secret key as long as the data, and we need one-time secret key. So in the end, we need single-use, long, random secret keys. The problem is the key distribution. The key must be printed, crafted, or saved on a physical object, and then the key could be copied during mechanical transport, and the transport is logistically expensive. Without the quantum regime, in the classical regime, the solution relies on trust. But we would like to go to the quantum regime. Over here you can see some photons. And I would like to introduce to you the quantum effect of entanglement. At first, in the quantum regime, when you measure things, you don't measure deterministic but probabilistic. So when you measure the photon 1 in a state, you measure it with the probability of alpha. The same goes with the photon 2, which is here probability of beta, and also with photon 3. But if photon 3 is a part of an entangled photon pair, and the measurement of the photon 4 depends on the previous measurement of photon 3. Einstein called this the spukhafte Fernwirkung, spooky action at distance. Okay, so now we have got some introduction. We will come to the quantum communication, and we can think of a simplified quantum communication scheme. It goes like this. There is a an entangled photon pair. Alice prepares or prepares not the state of the photon 1. Bob then copies the state of photon 2 to photon 3. Then Bob measures the photon 3, and as it is probabilistic, Bob repeats steps 2 and 3 until he's sure about his measurement. So he's sure about his measurement. The only problem is this scheme is oversimplified. It is possible with this scheme, if the scheme would be possible, the information distribution would be faster than light, and that contradicts the theory of relativity, which is bad. Okay. And down below you can see the original author, although I don't think he talked about entangled photon pairs. So it not only contradicts the theory of relativity, but there is also the no-cloning theorem. This no cloning theorem was just invented to counter the possibility of faster than light communication, and the proof depends on the linearity of quantum mechanics. Therefore, it's not very sophisticated. No, it is sophisticated. Anyway, what we have to keep in mind is that a single photon cannot be cloned. While this destroys our oversimplified quantum communication scheme, it also gives some kind of copy protections for single photons, single quantums. In our case, we would like to talk about photons, and it is important to remember that this copy protection is only for single photons. So when we have got 1,000 photons and measure 100 of them, then we have got still 900 photons that are not disturbed by the measurement, and nobody will miss the 100. So we need single photon sources. What are single photon sources? Single photon sources can be characterized by an experiment you see down below. So you take the photons of your light source, put it here in the beam splitter. A beam splitter, if it's perfect, directs 50% of the photons to this avalanche photodiode, and the other 50% to this photodiode, avalanche photodiode. The coincidence counter then measures the time difference between the events on this diode, or between the events on this diode and this diode. So, as you can see here, there are I've graphed 3 different sources. The first one is a light bulb on top here, which is a chaotic source, and in a certain time interval, it's very probable that when we have measured one event, that we measured a second event. As you can see, the photons are bunching here. Okay? Then we have got the laser. The laser is a coherent photon source, and the event an event is unrelated if any event has been previously measured. So as you can see, this line is quite straight. These photons neither bunch nor anti-bunch. The single photons, the true single photon source, which is perfect in theory, does anti-bunching. So as you can see, here's a certain time interval, and it is the probability that a second event is registered in this time interval is nearly 0. So, but for real single photon sources, we say that the second order correlation below 0.5 is a single photon source, and therefore it is in discussion if attenuated lasers can also be single photon sources, because as you can see here, when you drop every second photon of this measurement, you might get something similar to this green graph. Okay, so what are the possible sources? The possible single photon sources are quantum dots, which are atomic structures on a nanoscale, and some are engineered out of semiconductors, but there are also non-semiconductor quantum dots. Then there are optical parametric oscillators. This is a very interesting source because this OPO generates entangled photon pairs, and you can then measure one photon and know that there is a second photon flying around in a different state. It's then called a heralded photon source. You can use single photons, and you can use nitrogen vacancy centers in diamonds. These are, let's describe it so. There is a diamond made out of carbon, and one of the carbon atoms in this crystal is not carbon, but it's nitrogen. And these are very stable and very popular right now. Yeah. So, as conclusion, the anti-bunching behavior characterizes our single photon source, and the non-single photon sources would allow non-disturbing measurement of the state, which would, in the end, harm our security of our device. Okay. Here is a quantum key concept, quantum key distribution concept, and you have over here Alice. Alice prepare photon in a certain polarization, then sends this photon to the electro-optical modulator, which shifts the polarization at random. The photon is then sent over the quantum channel to Bob, where Bob modulates the incoming photo at random and then measure it with a polarizing beam splitter and detect it with a photodiode. The polarizing beam splitter is different from the beam splitter as it transmits or reflects photon. This is here it transmits, here it reflects a photon based on its polarization. So now Alice and Bob have done some measurement, and then Alice and Bob compare their random modulation of their EUM over a verifiable channel. This channel can be public but must not. But at least it must be verifiable. This in BB8084, there are two states for encoding and 2 states for randomizing. So here you can use 2 states, and here using also 2 states, and as an input there are also 2 states you can use. Okay, there are various protocols you can use. BB84 I just mentioned, it was the first protocol and is intended for 4 states. The E91 is used for uses entanglement from transmission, and the ZARC protocol is used in some commercial available quantum key distribution devices. Of course, the security depends on the implementation, and you might have seen the nice talk in 2007 at the Chaos Communication Congress where they show some practical attacks on quantum cryptography. So we have got got some quantum communication going on in the laboratory, which is awesome, but we would like to go beyond, and therefore we need to extend the range. One thing we could do is we can use the free space, aka the air, which has an advantage that is very flexible because air is nearly everywhere. And the disadvantage is that there's background light, like the sun or street lamps and when you have got a high photon count in your APD, the APD either burns out or just is saturated and doesn't detect any events. You can handle this, but it is a disadvantage. Another disadvantage is that the distribution medium, the air, is not very stable. There's, for example, fog or heavy rain or something like this, and this would degrade your key rate, and yeah, it's not what we would like to have. And there has been some experiments, and they reached, I think, about between 50 and 100 kilometers free space quantum communication. The main problem, for reaches beyond 100 kilometers, it's a problem that the Earth is not flat. You can't reach Tokyo from Hamburg without a very high tower or a satellite. So there was quantum communication proposed by satellite. And by satellite you're sending, for example, a single photon, an entangled photon pair source up with a satellite, and the satellite sends one photon to the receiver 1 and one photon to receiver 2. Each receiver measures then the photon, and through entanglement of the photons, the measurements are correlated. Down below you can see a paper that has been published that shows some more satellite schemes to communicate. Okay, then the next thing we could do is we could do quantum communication by fiber. The advantage is here that the signal in the fiber is relatively independent of the environment. I say relatively because every physicist that has shaken his fiber during an experiment knows how hard it can get to get any signal out of it. The fiber is of course flexible, but it is definitely not mobile. The good thing is also that you can use commercially available fibers, and these fibers are already in the ground and can be used as at will. So the disadvantage is that you can't use every wavelength, because the most wavelengths have a high loss in the fiber. The wavelengths that are used today for network traffic are around 800, around 1310, and around 1550. But even the last one has 0.2 dB damping per kilometer, and the reach is limited to about 100 kilometers. So what we should do now is to find a scheme to enhance this reach. One possibility is the trusted node concepts. Here you combine quantum transmission, like here in 1, 2, and 3, with classic transmissions like A and B. The problem is obvious, that you need to trust the persons or the machines or whatever works at this place here where the classical transmission takes place. It relies on trust that we also already had before, although this might be interesting test case for some things. Instead, you would like to reach the quantum repeater. The quantum repeater looks like this. It consists out of a quantum memory event, like here at 1, like here. It has got some entangled photon pairs element, a beam splitter, and 2 photodiodes. It is an idea published in this paper down below. So let's take a look at first at the beam splitter. It's entanglement swapping. Entanglement swapping means that you got here photon 1 and here photon 2, and you send both photons, which are part of entangled photon pairs, to this beam splitter. When these photons are indistinguishable, these photons bunch and end up at either this photodetector and this photodiode. When this photon bunch, the entanglement between these two and the entanglement between 2 and 3 is swapped, and afterwards you have got entanglement between 3 and 4. And thereby you have swapped an entanglement have reached a greater range. So now we've got entanglement, the entanglement swapping. And we would like to have also quantum memory element, because it enlightens a network synchronization, and it might be possible to connect this quantum memory element to other devices we would like to use. Okay, the quantum memory element. There has been defined some criteria for memory elements. As I said before, the wavelength is very important. The bandwidth is important, which means that the frequency interval in which photons would be still stored in the quantum memory. The fidelity describes the quality of the photon. So if I send in a photon in state R, the photon that comes out of the quantum memory element should also be in state R and not something else, because then it would be a random generator but not a memory element. And then the efficiency, that means how often I have to send in a photon to get a photon out. And of course, the storage time and the capacity is also important. Again, we can use quantum dots in V centers, in diamonds, atomic gases, and cold trapped atoms for quantum memory. Okay, quantum dots. You can see them here on the right-hand side. I think it's an atomic force microscopy, and these are the sizes, and this is out of semiconductors. So you have got a semiconductor of a certain lattice, and other semiconductors with similar but not the same lattice on top, and they bunch because they thereby reduce the energy, the surface energy. Okay, here we have got the conducting band, the band structure of the quantum dot. On the upper left, on the upper side is the conducting band, which is electron ensemble of electrons far away from the atomic core. And down below you got the valence electrons, which are the electrons near the atomic core. And then there are some states in this band. When then a photon comes into the quantum dot, it is absorbed and it generates an exciton. An exciton is an electron-hole pair. So because this quantum dot is biased, the hole, as you can see in the middle, is moved out of the quantum dot, and the electron can't recombine, at least for a certain time. It's not stable for hundreds of years. So then you have got this electron up there, and the incoming photon, and the information on the incoming photon and the information on the electron are correlated over polarization to spin correlation. So then for readout, you would bias the quantum dot again, but this time to move in some holes, as you can see down below. Then the holes are enter the quantum dot. Then the electron and one hole can combine, and photon will be sent out. If the fidelity is perfect, it is the same photon we have sent in. So in this paper, they mentioned that their fidelity was around 80%, plus minus 10, and they had only an efficiency of 20%, but others reach about to 97%, so which is a very high value, of course. The storage time is about 100 microseconds, and as just recently I read a paper, or at least an abstract, where they stored a photon for about 39 minutes, so it's sure enough probable long enough storage time. The bandwidth is 1 gigahertz, which I think is also wide enough, as you would like to entangle swap these photons, and for entangling swapping, as I might remind you, you need indistinguishable photons, and I'm not so sure where where you can't entangle where photons are not indistinguishable anymore, but I think 1 gigahertz is good enough for using it as a quantum memory. So as we have got quantum dots, the wavelengths of the quantum memory can be tuned as you wish. And for the capacity, you can do, of course, frequency multiplexing. And on the other hand, multi-photon storage is not likely, as they said in their paper. Okay, now we have got the quantum repeater. We have got here our quantum memory event, which stores photons for a certain time. And over here, the entangled photon pairs, which are useful for the entanglement swapping. If we combine a long chain of these quantum repeaters, we can reach any distance we would like to have. Okay. So, coming to my conclusion is, I told you something about the free space quantum communication, the quantum communication by fiber, and the quantum repeater with the main parts of the Bell state measurement and the quantum memory. If you liked the quantum communication, you also could take a look at quantum dots, which are a very interesting nanoscale structure, and at frequency down and up conversion. And yeah, I would like to thank you for your attention.
Now, if you have questions, there are mics there, and I think this one also works. Also, if you're on the stream, you can use IRC or Twitter. Any questions in the room? Okay, you, go ahead.
Yeah, you showed us with a repeater you have this beam splitter.
Yeah.
And you said the photons can bunch. How do they do that?
I don't know how, but the important point, because it's quantum mechanics, the important point is these photons come to the beam splitter, okay? And if they're indistinguishable, then they are bunched. This is the concept. Why they're bunched, it's not part of physics, I think, but it's in the quantum mechanics.
Okay, thank you.
Internet, please.
Internet.
Audio, please. Yeah, thanks. So I only have one question. How do you fix the static magnetic symmetry problem for the qubit? Does that problem even exist?
Excuse
so
me?
It's called static magnetic symmetry problem for the qubit.
Yes.
Does that exist?
I'm not so sure.
Okay. I think the one who posed the question wasn't so sure either, so
okay.
Never mind then.
Okay, you go ahead.
I don't know if I could follow everything. The problem is, would it be possible to have man-in-the-middle attacks? So if there is one untrusted step in this whole chain, would you detect it? Or is it attackable this way?
You mean with a quantum key distribution?
No, if you have a chain, but normally in a fiber you have to amplify the photons. This is done with some dotation now and classical way with some rare earth elements and something like this. But this is all classical, and they use stimulated emission to simply multiply the photons. So you would have one photon which has exactly the same quantum numbers, but it hasn't been measured. I never understood why this is not a problem for quantum cryptography.
I think you're talking about the no cloning theorem. You can't clone a single photon state perfectly.
As far as I could read, it only applies for systems with a Hamiltonian, and stimulated emission has a completely different Hamiltonian, which is not, where this is not applicable as simple as I think.
I don't think so. The no cloning theory says that you can't copy can't perfectly copy quantum in an arbitrary state. So you maybe generate a photon in a certain state because they have been produced before. So if I use the same process, I might get the same photon again, but you can't measure it perfectly.
But a laser, in my opinion, does exactly this. Simply copy.
No, they are not in the same state, and they don't share the same polarization in the laser.
Okay, that's the answer.
Okay.
Okay.
So can you say anything about the loss rate of the repeater, or is it perfect?
It's perfect, of course. Well, right now there is no quantum repeater. It is an active research topic, and right now the loss rates, I mean, the problem right now is that the quantum memory is not there, so we can't talk about a quantum repeater, but the loss rates are right now very high. So there's something to win which is actively researched.
Okay, thanks.
Please go ahead.
Hi. So usually when people talk about entanglement, they consider properties of particles, for example, photons, in two different locations. So the two particles have essentially pretty sharp locations, and then due to Heisenberg's uncertainty principle, of course, the momentum component of the particle's properties will be kind of broad. So the wavelength is not very sharply defined for the photons, which I think is fine in this case. But I'm saying, in the way people normally talk about entanglement, the space component is very sharp and the momentum component isn't. So my question is, in principle, I think you could also have a sharp momentum component and a very undefined space component. For example, if you look at electrons in carbon nanotubes, they might be delocalized essentially, and one might be going this way around the nanotube, the other one might be going the other way around. So my question is, have there been any experiments in using entanglement, not in space, but in momentum space? And if so, what could be practical applications for encryption and stuff? Because it should be possible by symmetry.
I can't remember a paper where this was described, so I don't know every paper, but it might be possible. So.
Okay, thanks.
Okay.
Do we have any more questions?
Yes, but it's the entanglement of the polarizations of two photons in two different locations.
Yeah.
And you could also have, for example, two electrons in the same position, in the same nanotube, and one is going counterclockwise, the other one's going clockwise, and that is two different locations in momentum space where they overlap in the direct conventional space. That's what I meant.
Okay.
Any more questions? Okay, go ahead.
I have only a very small question. So I was wondering, what is the problem with conserving the state when you, for example, when you use, when you try to save phantom states? You said that you can save it up to 100 microseconds or so. What is the problem? Why can you only save the state for such a short time?
In this paper, this is only one quantum array, so there might be others. I just mentioned there has been published a paper in November who said that they can save the state for about 39 minutes at room temperature, and I think for about 3 hours in cryogenic environment. The problem here is the decoherence of the electron. You see, this electron is not stable for arbitrary time, and after more time, I think they had problems to read it out.
Thank you very much.
I have a question concerning detectors. How do you actually detect a photon state and get the photon state out of the photon? So it's, I can't really imagine how to build a detector that can catch these different states. Do you do this with due to the beam splitter that you?
Yeah.
Okay.
When I talk about states, I mean just one certain property, like for example the polarization. Of course, you can use other properties, But the polarization you can catch with this polarizing beam splitter, which can differ between two polarization. And when it's of one polarization, it goes to the photodiode down below. And when it's of another polarization, it goes to the photodiode on the other side.
But if you use a photodiode, you never have actually one single photon detection. With an avalanche photodiode, you only can detect a bunch of photons coming to the diode. You're not able to detect one single photon because this will not cause the avalanche effect. So how do you come across this?
No, I mean, you use an avalanche diode for detecting this photon.
Yeah, but you can't detect one single photon with an avalanche.
You
need
do.
No,
I did.
Yeah, but you don't have one photon then, because it does not have single photon resolution, this type of detector.
It depends on what kind of avalanche diode you use, but there are avalanche photodiodes that are used for single photon detection. I'm very sure.
I'm very sure that there are.
Okay.
Any more questions? Anyone? No? Okay then, thank you. And another round of applause, please.